All right, this is part 3 of the 11.1 to 11.3 notes. We're focusing on the area of circles and sectors in this one. And I know you've seen before that the area of a circle is pi times the radius squared. If you click on this link, there's a really cool demonstration of why it works that way. I'd encourage you to watch that. And then we're talking also about the area of a sector. Now, a sector is an unbroken part of a circle. It's kind of like a piece of pie. So if I wanted to find this shaded sector right here, I could find the area of the entire circle, that's pi r squared, times x over 360, where x is this arc angle or central angle, same thing by definition. X over 360 tells us what fraction of the circle we're dealing with, times the area of the whole circle will give us the area that we want. I'd encourage you in this section to try to work through the examples. If you're stuck, you can follow along in the video for the ones that you need, or just look in the answer key. Some of these examples are definitely going to be harder than others. First example, you're told that the circumference of the circle is equal to 40, and you're trying to find the area. So what I would do first of all is go backwards and figure out the radius of this circle. The radius comes out exactly equal to 20 over pi. Once you have that, you can plug that radius back into the area formula, and you get an exact answer of 400 over pi, which is approximately 127.324, and our labels on these are going to be units squared. Here are our next two examples. The first one is just a sector, 50 over 360 times pi times 7 squared. Next one, our shaded area, is the area of the big circle minus the area of the small circle. The radius for the big circle is 6. The radius for the small circle is 3, so it's going to be a 36 pi minus a 9 pi, which gives us about, or 27 pi, which is about 84.82 units squared. Number 12, or the next one, 12 is the diameter of the circle, which means that the radius of the circle is 6. So the total area of the circle would be 36 pi, but then we have to subtract away the area of the square. The 12 is the diagonal of the square. And to find the area, when you know the diagonal, you can take diagonal squared divided by 2. Or if you wanted to use 45, 45, 90 triangle, both of those are 6 root 2. Multiply that by itself. Either way, you get the area of the square is 72. And when you subtract those exact values, you get about 41.10. And the next one, we don't have to subtract anything this time. The shaded area is the area of that regular triangle. 8's the diameter of the circle, which means that 4 is the radius of the circle. This is a regular triangle. I know there was no markings to indicate that, but we're going on the fact, or the assumption, that these are going to be regular shapes, and I would normally verbalize that to you in person. So these lengths are both going to be 4, and if I were to draw in the other radius, it would give us 3 of these triangles that are all congruent to each other. Find the area of one, multiply it by 3, we have the entire area. If I just focus on this yellow one, I have side of 4, 360 divided by 3 means that the angle between them is 120, so the area of this one yellow triangle is 4 times the sine of 120 times a half. Triple that, so here's my setup for that, and I get about 20.78 units squared. Next one. I know it's kind of hard to see in the original drawing, but there is a right angle in that lower corner, so this is a right trapezoid. So our shaded area is going to be the area of the entire trapezoid minus the area of that circle that's been taken away. The trapezoid is the average of the bases times the height. So if we drop down this altitude over here on the right, I know that the hypotenuse was 10. This height has to be 8 again. So with Pythagorean theorem, we're realizing it's a Pythagorean triple. This length is 6, making the whole bottom base equal to 18. That's why the average of the two bases is 15 times the height of 8. The area of the whole trapezoid is 120. 8 is the height of the trapezoid. It is the diameter of the circle, which means the radius is 4. So the area of the circle cut away is 16 pi. Subtract those and we get about 69.735. The next one, we have one of these areas of a segment of an arc. That's the official name. Sometimes I'll call those like little wings on the outside. So imagine that we originally had this whole sector right here in yellow. Find the area of that entire sector. We would do 80 over 360 times pi times 5 squared, because 5 would be the radius, that'd be the whole thing. But then we'd have to subtract away this green part because this isn't included in that little segment of the sector that we have over there. So to find the area of this green one, we would subtract away 1/2 times 5 times the sine of 80 degrees. When you subtract the whole sector minus this triangle, we get about 5.14 units squared. Dog on a leash is an interesting problem. I have a YouTube video link. I'd encourage you to watch that. Here's our answer to the first one. Spend some time, see if you can work your way through it, struggle through it a little bit. You can figure it out on your own. That's outstanding. This is a tough problem to get initially, but once you understand the concept, the calculations aren't hard. I'll scroll down a little bit. Here's my calculations for the next example where the dog is on a leash attached to the corner. So the dog can rotate around, get to different parts of the building, and I have these different regions. So this yellow region represents 3/4 of a circle. This little green region is just 1/4 of a circle. And then we also have this other region over here. I didn't draw that very well. It should have stopped a little earlier. That's another 1/4 of a circle with a radius of 4. So we get about 113 pi for this one. And we're down to our last few examples here. The first one, these two circles both pass through the centers of the other circles. So this 15 splits up as 5, 5, and 5. So the radius of each circle is 5. The shaded area could be viewed as 1, 2 regular triangles. That's what I have right here, plus 1, 2, 3, 4 of those segments or little wings on the outside. And that's what I'm looking at right there. So to find the area of the two triangles, to find the area of those little green parts, I find an entire sector, subtract away the area of one of those triangles, and there are 4 of them, so I'm going to do my work on the inside, distribute the 4. Here's my nice exact answer, simplified for my final answer. The next one, to find the shaded region, we're going to take the area of the hexagon minus the area of the circle, but only 4 out of those 6 regions are shaded, so it's 2/3 of the hexagon minus the circle. The area of the hexagon I have up here. Nice thing about a hexagon is it's a very special shape. It is made up of 6 equilateral triangles. So if I were to draw in diagonal, 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 all 6 of those triangles are going to be regular triangles, so I could find the area of one of them, multiply it by 6, and we have the entire thing. That's what I did up here to find the area of hexagon. The area of the circle is just pi times the radius squared, so we're subtracting them times 2/3, and here's a nice exact answer for that one. This one doesn't say it again, but that is a regular pentagon, so the shaded area is pentagon minus circle. There's my shaded area idea. I drew in the radius to this point, to this vertex. It creates this yellow triangle. I use trig to find x. Then the area of this yellow triangle is 18 over tangent of 54. There are 10 of these triangles making up the entire shape, 2 on each one of the sides, so I multiply that by 10 to get the area of the entire pentagon. The area of the circle is just 36 pi, so if we subtract those, there's our shaded region. And lastly, the area here is the area of the circle minus the area of the hexagon. The circle is 25 pi, the hexagon is 6 times 5 squared root 3 over 4. There's our equation. This should look familiar. This is the area of one of the regular triangles. For example, this one right here. And since the regular hexagon is made up of 6 of those regular triangles, I multiplied it by 6, simplified it a little bit, and there is our shaded area.